Hello everyone, and welcome to my session combining AI in consumer devices using a scalable vector DSP. My name is Koren and I'm a machine learning system engineer at CEVA DSP. CEVA focus has been on creating solutions to address both wireless connectivity, such as Bluetooth and Wi-Fi, and smart sensing, like vision and speech recognition. We have created product that was basically focused on these individual technologies. But as we see today in the markets, more smart devices support and utilize many kinds of technologies. We have realized our product need to have the ability to process multiple sensor types. We needed to develop a product that will be in the middle and connect all those sensors together in one platform. This is the reason why CEVA decided to develop the industry's first high-performance sensor hub DSP architecture called the SensPro. CEVA SensPro is designed to serve as a hub for processing and fusing data from multiple sensors, including camera, microphones, radar, LiDAR, and more. SensPro architecture is highly configurable and self-contained, combining scalar and vector processing for floating point and fixed point data types, as well as deep learning inferencing. SensPro offers the processing capacity required for sound, imaging, and deep neural network inference. SensPro scalability includes wide range of self-contained processors, scaling in performance for a broad range of end markets. As you can see in the table, the SensPro 50 is the smallest DSP, developed mainly for IoT and smart devices. The most powerful one in the group is the SensPro 1000, with 1K multipliers, developed for automotive and robotics markets. The SensPro DSP is not coming by itself. It is accompanied by a rich software by the name of CDNN, CEVA Deep Neural Network. The CDNN is a graph-based computation framework. It is CEVA proprietary software for AI inferencing and future retraining. It is fully optimized for CEVA architecture and provides high performance and accuracy capabilities. It is a mature and robust solution with over 5 years of experience and supports a variety of framework models, like Onyx, Caffe models, TensorFlow, and TensorFlow Lite. In this slide, we can see an overview that illustrates the CDNN development flow. It is divided to 3 different stages. On the left-hand side, you can see the first stage, which is the offline training. Users will develop and train their networks by using one of the common frameworks, like Caffe, Onyx, TensorFlow, or TensorFlow Lite. After the network has been fully trained, the user can create his own floating point network model. This model contains the network structure and the floating point weights. After the floating point model is ready, we can start the second stage, which is the offline optimization. In this stage, the user uploads the model itself with the floating point weights into the CDNN. The CDNN basically performs what we call the graph compilation or the generation phase, which takes the network model and optimizes it by applying fusion technique as well as other optimization techniques. In this stage, the CDNN pretty much prepares the model for the execution of CEVA hardware. What it does, among other things, is of course the quantization process. This process converts the floating point network to a fixed point network and applies a lot of optimization for the memory consumption of the entire network. The output of the offline optimization stage is a binary file which is basically burned into the CEVA hardware, and it's a recipe for running the network. The CDNN creates it shortly once the compilation or generation process is completed. Now we can start the last stage, which is the real-time inference. We basically feed it with an input image, runs the network on the hardware, and produce results. This is a brief overview of how the CDNN works. As we all know, customer developed an AI engine is a growing trend of innovative architecture driven by a software and application specific. However, developing software framework per engine is not cost effective and it's very resources demanding. On the other side, CDNN offers a comprehensive and mature deep neural network layer support, thanks to many years of customer engagement in various industries. Therefore, CEVA decided to develop the CDNN invite feature. This feature enables unified programming model with any customer AI. The customer can be focused on his architecture while benefiting from mature and up-to-date inferencing optimizer. In addition, it can dispatch an unsupported deep neural network layers to CEVA SensePro DSP. The CDNN invite feature includes two levels of API, CDNN device API and CDNN node API. The feature enables customer AI nodes and engines to connect to the CDNN frameworks and benefits from the support of over 300 different neural networks, benefit from graph compiler optimization and efficient runtime edge computing and memory allocation. The CDNN invite feature includes three guides. The first guide is the specification document, which defines functionality and syntax for the generation and runtime stages. The second guide is the developer guides, which include workflow, example, and sequence diagrams. The last guide is the integration guide, which includes instruction of how to use and integrate the customer AI node and engine to the customer applications. Before deep diving in the CDNN invite feature, let's review some graph terms defined by CEVA, which are related to the CDNN invite. You can see in the graph that we have the node, in the node we have the operation, and inside the operation we have the operator. Each neural graph node can be defined by one operation or more operation in case of node fusion. The operator are selected and used by the operation. The operators are functions that perform calculation. There are three types of operators. Naive operators that are using C code running on a PC device, on a general device. Optimized operators that are using VEXI code running on CEVA DSP devices. And the last one is the hardware operators, which control the engines and execute its capabilities. As mentioned before, the CDNN invite API has two levels of APIs, the device API and node API. Let's review the device API first. The device API acts as an interface between a custom AI engine device and the CDNN. In the slide, you can see illustration of two modes of the CDNN. On the left side, you can see the native-only mode. By this mode, the CDNN is connected only to the SensePro device. On the right, you can see the custom AI mode, which set the CDNN to connect to the SensePro device and using the device API to connect to a custom engine device. This custom engine hardware is defined and developed only by the customer, and the CDNN is not aware of it. The device API includes software hierarchy that defines different levels of interactions with the CDNN. As can be seen in the graph here, we have three levels of interactions. The top level interaction is the CDNN customer device. This is an interface class which enables the CDNN to control and manage a custom AI engine device. Each device holds a database of its supported operation operators. For example, we can see here that this specific device supports convolution, altwise, and pooling operations. The CDNN custom device responsible for the operation fusion configuration. And in addition, it manages the device internal memory and DMA transactions. Each operation has its own operators. Here we can see that the convolution operation supports update operation, execute operation, and set operation data operators. Beneath the CDNN custom device, we have the CDNN operation. The operation is implemented per device, it's a device specific, and represents the device hardware capabilities. The operation can be queried if this device supports certain properties, such as input-output data type and kernel size. In other words, if the CDNN wants to know if a custom device can perform, for example, a convolution operation with a specific parameters as defined in the network, the CDNN will request from the custom device a convolution operation and validate those specific parameters with it. If the operation returns that the parameters are supported, the CDNN will set that this operation can be executed by this custom device. In addition, the operation acts as an interface between the node and the hardware-specific operators. This means that the operation passes the operators to the node, and the node is executing the operators. The lowest level of interaction with the CDNN, as defined by the CDNN invite, is the CDNN operators. The operators are functions with one or more inputs and outputs meant to perform a calculation. This calculation is executed on the device hardware. Therefore, the operators are written for a specific hardware and depends on the device capabilities. As mentioned before, we have three types of operators. One is the naive operators that use C code and run on a general device. The second one is the optimized operators that use VEC code and run on CEVA DSP devices. The last one is the hardware operators that control the engines and execute its capabilities. The operators are selected and used by the operation. The operation manages and selects the best operators for specific parameters. Let's take, for example, a specific hardware operators called set operation data. The operator sends the operation persistent data generated in the offline stage back to the device in the runtime stage. In this slide, I'll review a high-level sequence diagram of the device API flow during the offline generation phase. On the diagram right side, you can see a blue area that illustrates the device API. It contains a custom device object, an operation object that is related to this custom device. On the diagram left side, you can see the user and the CDNN generator, which is the CDNN application for the offline phase. The generation phase is divided to three main stages: initialize, execute, and finalize. During the initialize stage, the CDNN generator queries the custom device to determine if it can be used to run the network nodes. In other words, the CDNN generator creates for each node a database of operation that can be executed in runtime. During the execute stage, the CDNN generator runs the network nodes in floating point to determine the optimal way to quantize the network parameters. During the finalize stage, first, the CDNN generator determines if a node fusion option exists. Then, it creates a device operation that will be executed in runtime with specific parameters. Afterwards, it performs quantization on the network parameters and encodes the operation data. It releases the allocated memory and generates the CDNN binary file as called the queue data. In this slide, I will go over a high-level sequence diagram of the device API flow during the runtime phase, the inference phase. As was seen in the slide before, the blue area on the right illustrates the device API, and on the left you can see the user and the CDNN runtime application. As you can see, the runtime phase is also divided to the same three main stages: initialize, execute, and finalize. During the initialize stage, the CDNN creates for each node a device operation based on the operation type and parameters. It decodes the operation parameters from the operation data, and for each node, it gets the operation signature. The operation signature is a structure that contains the operation operator that will be executed in the execute stage. During the execute stage, the CDNN runs the node operators, which in this example, you can see the set operation data, update conv operation, and execute operation. Using the set operation data, the CDNN set the address to the operation data in the queue data file. It updates the operation parameters in runtime via the update operation operator and execute the operation via the execute operation operator. During the final stage, the CDNN get the operation performance matrix and release all the allocated memory. By the end of this stage, the CDNN gets the network output file and the profiler report. Okay, so I reviewed the first level of API under the CDNN invite, which is the device API. And let's continue to the second level API, that is the node API. So as you can see in the graph, the node API also defines 3 levels of interactions with the CDNN. The top level is the CDNN custom node. Beneath you can see the operation level, and on the bottom you can see the CDNN operator level. The CDNN custom node is an interface class that enables customer to integrate new neural network nodes that are not natively supported by the CDNN. The node API supports different types of operators, such as naive, optimized, and hardware operators, as I mentioned before. Therefore, the customer can develop a new neural node that will be executed on custom AI engines or on CEVA DSP. In addition, the node API supports custom node parsing of multiple network formats from the common frameworks as Caffe, TensorFlow, and Onyx. The node API as well as the device API use the CDNN operation and operators, and by that the CDNN execute the node using the operation and operators received from the custom device. In this slide, I will go over the Node API development flow, which is a flow recommended by CEVA to develop a custom node. First, it's recommended to develop a parser plugin. The parser plugin can be developed for different network format, and it's responsible to parse the custom node parameters from the network model. Afterwards, it's recommended to develop a new operator. The naive floating point operators will be used in generation stage to execute floating point network and to quantize the network parameters. The optimized operators that are written in VEXI code for 8-bit and 60-bit will be used to execute in runtime stage. Develop new node operation. The operation chooses the best possible operator that supports the operation parameter. For example, if the user implemented different operators for different filter size, the operation is the object that is responsible for selecting the right operator. Afterwards, it's recommended to develop a new custom node that the CDNN communicates with. This is the custom node object that include system code for CDNN operations and CDNN operator, memory allocations, and weights ordering. Afterwards, implement the node library application interface function. This is functions that are responsible for creating the custom node, custom operation, and custom operator object and add them to the CDNN. And the last stage is to integrate the user node into the customer application. So that brings us to recap. We introduced the SensePro DSP, the world's first high-performance sensor hub DSP for AI, computer vision, and sensor fusion applications. The SensePro DSP cores are complemented by CDNN, a highly optimized graph compiler and runtime framework. We introduced with the CDNN API features that enable users to connect custom AI nodes and engines to benefit from the wide neural network support and optimization of the CDNN framework. And we deep dive to the device API and node API, which provide the software architecture to control and manage a custom AI engine. Thank you for your participation and listening.